So in the last video, I gave you a little introduction to some examples of how to convert from binary to decimal and back. Today, I want to show you a process for doing this in a sort of objective way, so that if you have trouble figuring out which number might be the number to put in there, you have this algorithm or this process to fall back on. So let's use the example that we started with before, which is the number 26. Let's convert that to binary the way we did before. We had 1, 2, 4, 8, 16, 32. These are all our powers of 2. And we just sort of guess which one is going to fit best. So 32 is too big, so we need 16. So this is 16 plus something, plus 10. And then we do the same thing again. With 10, we figure out which one's going to fit. 8 will fit. So it's 16 plus 8 plus something left over, which is 2. And 2 is a power of 2. And that's the way we do this. Now the process that I'm going to teach you is actually the opposite of this. Instead of finding out the biggest number, we want to find out the smallest number. How do you find out the smallest number? Well, the smallest number is either going to be a 1 or a 2. And we don't know which one it's going to be, but you can look at this number and you can say to yourself, is this going to have a 1 in it or is it going to have a 2 in it? Which one is going to be the smallest number? How would you figure that out? Well, you can do that by deciding if it's odd or even. If it's an odd number, you need 2 to the power of 0. If it's an even number, you don't need 2 to the power of 0. The first and smallest number you have in there is 2 to the power of 1. And so we can tell by dividing by 2 whether it's odd or even. And then we take the remainders, and the remainders will tell us whether or not there's a value in the place value before that. Watch this. So 2 to the 26, 26 divided by 2 is 13 with a remainder of 0. That remainder of 0 tells us that it was an even number, and if it's an even number, that tells us that there's a 0 in the 2 to the 0 place value. That's it. So that's our first bit, or our last bit. Then we do the same thing again with the next value. So 13 divided by 2 is actually going to be 26 divided by 4, and that'll tell us whether there is a bit in the 2 to the power of 1 place. So 13 divided by 2 is 6 with a remainder of 1. That tells us there's a 2 in the number because we divided by 2 and we got a remainder. Now we do the same thing again. 6 divided by 2 is 3, remainder 0. So there's no, so these are our 1s, our 2s, our 4s. There's no 4s in that number. Then we take the 3 divided by 2 and we get 1, remainder 1. So there is an 8 in that number. And now the last thing we have to do is 1 divided by 2 is 0, remainder 1. And that means, this 1 means there's a 16 in that value. When we have 0 here, we know we're done. Because we can't do 0 divided by 2. I mean, we could. It would be 0, remainder 0. We just get zeros all the way down here. So that 0 tells us that we're done. This repeated division by 2 is our way to figure out what bits are going to be in that number. And it's analogous to how you would do this in a base 10 system. To figure out what numbers are in base 10, you do repeated division by 10, and you'd get the numbers back. I'll give you an example of that later. But to find the number here, now that we finish this, we start with this last number that corresponds to this 0, and we read upwards, because that's our 16's place, our 8's, our 4's, our 2's, our 1's. 1, 1, 0, 1, 0, which is the number that we got before. Let's do another example. Let's take a number that we haven't seen before that might be a bit more complicated and difficult. Let's do 127. 127 is a big number. How many 16s are in it? How many 32s are in it? How many 64s are in it? It would be difficult and it would take a long time to do that with that process that we had before. So now with the new algorithm, all we have to do is do repeated divisions by 2. So 127 divided by 2, it's going to be 64, would be 128. So this is 63, right? 63 would give you 126, so that's a remainder of 1. 63 divided by 2, I see this is going to be a problem. So 62 would be 31, remainder 1. 31 divided by 2. So you can see each time we take whatever our quotient is and we divide it by 2 again. Because this is the number divided by 4, right? And the number divided by 8, and the number divided by 16. So 31 divided by 2 is 15, remainder 1. 15 divided by 2 is 7, remainder 1. 7 divided by 2 would be 3, remainder 1. 3 divided by 2 is 1, remainder 1. And 1 divided by 2 is 0, remainder 1. This is always going to be our last step. We're always going to get 1 divided by 2 is 0, remainder 1, because we need a 1 at the beginning to start our number off. Anyway, 1, 1, 1, 1, look at all these 1s. So the number 127 is 1, 1, 1, 1, 1, 1, 1, 1. It's 1 and 2 and 4 and 8 and 16 and 32 and 64 and 128. And that is the way to do this in our second example. So now what I'm going to do is I'm going to show you a few examples of how to do this in base 10 to see how it works properly. What's the analog of that in base 10?